this is our investigation on more graphing rational functions. So up here at the top, we've been given the function in two forms, in multiplied out form, and then over here in factored form as well. So when given a rational function, the first thing we want to do is going to be to factor everything. That way we can look and see if any factors will reduce and any factors that will not reduce. We already gave this to you in factored form, so you didn't have to factor yourself. Okay, next thing we're going to do is we're going to find the x value of any wholes. And set those factors that reduce out equal to 0 and solve them. So this x plus 4 here reduced out. So the x coordinate of the whole would be -4. Now we've got to find the y coordinate of the whole. So to find the y value of the whole, we are going to substitute the x value that we just got, the -4, back into the reduced out equation up here and see what we get when we do that. So on the top of the fraction, we now have a 1. On the bottom of the equation, we plug in -4 for both of those x's. And then when we reduce, that would give us 1/9 for the y value of the whole. And then we can go ahead up here on the graph. I made a nice hole there to show that you can see that it's a hole. Next, we want to find the vertical asymptotes. So to find the vertical asymptote, we're going to look at these factors down here that didn't reduce out in the denominator, only the denominator, and we're going to set those factors equal to 0 and solve them, because division by 0 gives us problems. So when I do that, I'm going to get 2 asymptotes because I have 2 factors on the bottom that didn't reduce out, and my 2 x asymptotes are going to be x equals 1/2 and x equals -3, and those are shown up here in the graph on purple as well. Next, I'm going to just state the discontinuities, and I already know what all of them are. They are the vertical asymptotes and the wholes, or all of the original zeros of the denominator. So whether they reduced out or not, if they were in the bottom, this 1/2, the -3, and the -4 would all make division by 0. So they're all going to be listed as discontinuities. X equals -4 will be a point discontinuity because that was one that reduced out, it was removable. And x equals 1/2 and x equals -3 will be infinite discontinuities because they did not reduce out, they were the vertical asymptote. We do have a horizontal asymptote in this graph, but that does not affect the discontinuities at all. Next thing we need to do is to find the x-intercepts or zeros. So since when 0 on top of a fraction creates 0 as the reduced version, we need to look at our reduced version and set the top equal to 0. So for this one, there was nothing left on the top but 1, so 1 never equals 0, so this is not going to have an x-intercept. To find the y-intercept, for any coordinate on the y-axis, the x value will be 0, so I'm just going to plug in x equals 0, and I can plug that into either form right here. I would get the same answer. I get -1/3 when I simplify that, so 0, -1/3 is my y-intercept. What we still don't know is anything about the horizontal asymptote or the end behavior of this. So just looking up here at the graph, I can see my horizontal asymptote looks like it's at y equals 0, which means my end behavior, both ends of the graph, the right end and the left end over here as x goes to positive or negative infinity, are also both approaching 0. So where we're going to advance in this lesson is see how could we tell from looking at the equation that the horizontal asymptote would be y equals 0. Since the horizontal asymptote and the end behavior are really the same thing, we want to think what would happen to the y values in our equation if we plugged in really big x's for all the x values. So if we did that, this would be 2 times some giant number minus 1, and a giant number plus 3, and then we'd multiply those 2 giant numbers together, and we would have 1 over something that's really big. If I take 1 and divide it by something that's really big, it's going to turn really small. So we say this approaches 0, which is why up here my end behavior is y approaches 0, and my horizontal asymptote is y equals 0. So what is the relationship between the horizontal asymptote and the end behavior for a rational function? So the horizontal asymptote identifies the value the graph approaches at its ends. So really, they're going to have the same numerical value. All right, got to be a lot of reading in this next part, sorry. Here's the overall gist of it. Inputting large values of x gives the end behavior of a function and determines what happens on the left and right ends of the graph. Two things can happen in a rational graph. The graph will either level out to a horizontal asymptote, or it will keep growing and approach positive or negative infinity. The end behavior tells us what is happening on the left and right ends of the graph, not in the middle. So sometimes the graph will cross a horizontal asymptote or a slant asymptote. We'll learn what those are in just a second. To find the equation of a horizontal or slant asymptote, you would divide the original equation in the form it was given, and then it would turn into some other function with another small rational next to it as a remainder. So for really big x's, the remainder is going to be insignificant, so we can ignore it. The equation of the horizontal or slant asymptote is y equal to the answer to the division without the remainder. So for a horizontal asymptote, if the degree of the numerator is less than or equal to the degree of the denominator, the graph will have a horizontal asymptote. So think about that. That means there's the same number of x's on the top and bottom, or there's more x's on the bottom. That's going to result in a horizontal asymptote. This is because when you input large values of x, the y values get closer and closer to a fixed number, and that horizontal asymptote is y equals this number. So if the degree of the numerator and denominator are equal, then the horizontal asymptote is going to be the ratio of the leading coefficients. Whereas if the degree of the bottom is bigger, like in the example we just did, the horizontal asymptote is going to be 0. Slant asymptotes. If the degree of the numerator is 1 more than the degree of the bottom, so like you have an x squared over an x, then when you input large values of x, you're going to wind up with the top winning out and you will get large values of y. When this happens, the graph will have a slant asymptote, where the asymptote is a diagonal line instead of a flat or a horizontal line. We will not write the equations for these this year, but you should recognize that they exist and they might come up when you're working. You would just divide to find them algebraically, and we'll do that in pre-calculus. The last bit will be to plot the points on the graph, and to do that, you're just going to plug in x's to find y's. The easiest way to do this is to use the table on your calculator or on Desmos. You can also make sure you use the fraction button when you input these functions because they can be complicated looking. You can use trace and you can type in x values that you want. You can make sure you plot a few points on each branch, and if there are any relative extrema, any max or mins or turning points, that you use your calculator or Desmos and actually find the coordinates of those turning points using either Desmos or Calc on your calculator or GSolve if you have a Casio. The other thing to notice in your table is what does the calculator give as the y values for vertical asymptotes and whole? And the calculator is going to say error. Now, when we write things in our tables, we would write does not exist instead of error, but the calculator says error. So on example 2 here, we want to graph this. There are some things we should be able to do without using our calculator. And then when we actually go to make the graph, we use our calculator. So the first thing we want to do is make sure we're in factored form, which we are. And then we want to look at what we can reduce. This x minus 3 here can reduce out, which means it's going to create a hole when x equals 3. To get the y coordinate of that hole, we're then going to plug x equals 3 into the reduced version, which gives us 10/3 when we simplify. So that's the y value of the hole. So I can go ahead and plot that hole on the graph. I can find the zeros also without my calculator. The 0 happens when the top of the fraction equals 0 in the reduced form. So if the top equals 0 and x equals -1/3, I usually write zeros as x equals, whereas I write x-intercept, which is the same idea, in coordinate form. And then I went ahead and I plotted a point right here at x equals -1/3 on the x-axis. To find the y-intercept, I'm going to plug in x equals 0, because the x value is always 0 in a y-intercept. So when I plug in 0 to the reduced form, it gives me y equals -1/3. So I went ahead and plotted that point as a y-intercept as well. To find the vertical asymptotes, I want to look at where the bottom was equal to 0 that did not reduce out of the function. So that gives me x equals 3/2. So I went ahead and put a vertical asymptote on my graph at x equals 1.5. Now remember, to find the horizontal asymptote, we're going to look at, in the reduced form, what happens with our top and bottom. I've got 3x plus 1 over 2x minus 3. So essentially, it's 3x over 2x if I'm looking at the big powers. 3x over 2x would reduce to 3/2. So that 3/2 when I reduce is going to be my horizontal asymptote, which would be y equals 3/2. And I can draw a line up here at y equals 1.5 as my horizontal asymptote. Now, since this is the horizontal asymptote, it also tells me my end of behavior, which as both x approaches positive and negative infinity, y will approach 3/2 the value of the asymptote. You should be able to tell the domain and range. The domain is x is not equal to 3 or the 3/2, the 2 zeros of the original problem on the denominator. But to be able to tell what the range is going to be, I have to know what the graph looks like. And to know what the graph looks like, I'm always going to let you use your calculator. So I'm in Desmos, and you can just Google it or click the link that you have on the home page. This is the Virginia SOL version that you'd be allowed to use on the SOL test if you were taking it, but they're all pretty similar for this part. So I start out literally just typing in the top of the function, and you'll notice the graph starts popping up as you go. Once I have the top of the function, if I hit the division key, it automatically makes it the pretty print fraction, and I can then type the rest. So I've got on the bottom x minus 3 and 2x minus 3. If you're doing this on your graphing calculator, it's extremely important that you either double parenthesis the top and the bottom if you don't have the pretty print, or you just make sure. So looking at my graph right here, it shows me my x-intercept was -1/3. It shows me my y-intercept was -1/3. But you also might be thinking, well, where is that hole at x equals 3? So if you put your cursor on the curve, you can follow points along that you could then plot on your paper. And as you get close here to x equals 3, you can see when x equals 3, it's undefined. And it actually makes a little hole, but then as soon as you move away, it's gone. So you can either trace along the curve and get those points that way, however you want to, or you can come up here at the little gear and you can change this to a table instead. And the table will give you some of the points. If you wanted any more points, suppose you wanted x equals 3, you just type in 3 and it gives you the value. You type in 4 and it gives you the value. So you can get a table of function values that way as well. And then we're just going to plot those on our paper. So I just plotted. I made sure I had at least 3 points on each branch right here where I was graphing. I can still see the hole. I can still see the x and y intercepts. And now I'm ready to say my range. So for the range, I want to look at the graph from bottom to top, and I want to pay any attention to any horizontal asymptotes or the y values of any holes. So as I'm working down forever, I'm fine, I'm over here, and then I hit this asymptote. So y cannot be equal to 3/2 because that was my y value of my horizontal asymptote. Then over here, I pick up on the other side and I'm going up, and now y can't be equal to the y value of this hole, which was at 10/3. And then it keeps going up from there. So my range is y is not equal to 3/2 and 10/3. Again, everything with the exception of the range and this actual putting points on the graph, I could do without a calculator, but you'll always have a calculator to do those last 2 steps. So in example 3 here, we've given you a function, and we've already given you the picture of it because this one looks a little different than others. This one's going to actually have a slanted asymptote. So I want you to try and factor up here and then use your equation to see if there's any holes, x-intercepts, y-intercepts, vertical asymptote. There's not going to be a horizontal asymptote because it does not flatten out. Again, if you divided this, you'd have x squared over x, which would give you a reducing of x, which is going to be a diagonal line. There's other things involved as far as a y-intercept slope changes, but we're not going to worry about those, just to know that it's not horizontal. In order to tell where this thing is increasing or decreasing, you're going to have to look at these turning points right here so that you can see the change from decreasing to increasing. So go ahead and put this equation also into Desmos or on your graphing calculator and find those turning points, and then use them to help write the domain and range as well. So pause the video, will you give that a try, and then we will check your answer together. All right, so I write the top in factored form here, and the bottom was x plus 1. So since nothing reduces from the top and bottom, there are no holes. The x-intercepts, or where the top of the fraction equals 0, I would have two of those, one from this and one from this. So I have x equals 1 and x equals 2. For the y-intercept, I plug in 0 for x. It's easy to do it in the original version here, and everything would wipe out except for this 2 over 1. So y equals 2 is the horizontal asymptote. The vertical asymptote, I'm sorry, I said the vertical horizontal asymptote. I think that's the y-intercept. The vertical asymptote is where the bottom equals 0 that doesn't reduce out. So that would give us x equals -1 is where the bottom equals 0. So that's a vertical asymptote there. There's no horizontal asymptote, again, because there's more x's on the top or a higher degree on the top than the bottom. To tell where it's increasing, that's where I'm going up from left to right. So I'm increasing along this piece right here. So from x is -infinity until I get to this peak. Well, I can't tell exactly where that peak is without going to Desmos. So let's go ahead and look at Desmos. So I type this into Desmos, and I can't see the bottom piece. I can either just move my cursor and drag. Then if I click, it's going to tell me the critical points. So that point that it's just plotted on there with the gray dot is the maximum point in that area. And as I was looking up here before, if I click, it will give me all the important points, the y-intercept, the x-intercepts, and any turning points. So that is the value of the x turning point. Is the x value of that turning point is 1.449, and the y value is -0.1. So let's go back to my graph. So I increased until I got to this x value, and then I decreased. So I was decreasing from -3.44 until I got to -1, which was the asymptote. Then I had to pick up my pencil to come over on this piece where I was decreasing as well. So I'm decreasing from -1 until I got to my minimum point, which was at x equals 1.44. And then I'm increasing again from x equals 1.44 until infinity. You do have to split these into two separate pieces because it's not a connected graph. X equals -1 does not exist in the domain. Your domain, or your end behavior, as x goes to infinity, that's the right side of the graph. Y was going towards positive infinity. And as x goes to a negative infinity, that's the left side of the graph. Y was going down here towards negative infinity. Our domain, x is not equal to -1 because that's the only spot in the original problem that would give you division by 0. And then for the range in this one, it's a little more challenging. We go from -infinity until we get to this peak. And the y value of that peak, which we'd use for the range, is the -9.89 number. So I can say y is less than or equal to -9.89. I just have to say or. Then my other peak over here, this U shape, y would be greater than or equal to the y value of the minimum, which was the -0.10. I could also write that in interval notation with the parentheses around everything. Oops, that actually shouldn't be parentheses. Let me fix that. These guys should be brackets because I do equal them. All right, let us know if you have any questions on those, and good luck with your practice.